In today's video, we are actually going to build our oscilloscope project on a breadboard. We're going to boot it up, write some firmware, write some drivers, get it all on there, and just do the initial prototyping stage for our project. So prototyping comes directly after the design stage. We already did the electronics design for this in a previous video, so you can go check that out if you're interested. The point of the prototyping stage is threefold. So number one, we want to make sure that the wiring decisions we made in the electronics design stage are appropriate and they're actually going to work out for us. Number two, we want to verify that our hardware devices work and the hardware devices behave how we expect them to. So, of course, we do design decisions based on datasheets and based on specifications, but how devices behave in the real world can sometimes be different to what we anticipate. And number three is we want to do some initial firmware architecture and sort of just lay a foundation for the rest of the project. So what we're not going to do is rush to a PCB design. We want to build this on a breadboard first to make sure that our design actually works. And after that, we know, okay, so if I wire this on a PCB pretty much exactly how it's done on my schematic and exactly how it's done on the breadboard, then it should work provided I do my PCB design correctly. This is just a verification stage of things that we've already done. And it allows us to lay a foundation and actually start writing some firmware, right? So we didn't actually write any firmware in the design stage. Now we're going to write some firmware. The key thing in the prototype stage is to take our design. So this is our full-fledged design, right? This is what I anticipate is going to be on our PCB. And what we have to do is cut it down to a point where it is appropriate to build on a breadboard, and it sort of captures the majority of what the system's functionality is going to be. So just as an example, we're looking for things to gut out here that we don't need. This USB surface mount housing, we won't need. This voltage regulator, we won't need. This STM32, programmer, we won't need. Why? Because we're going to replace this STM surface mount microcontroller with a development board. And the development board has USB, it has a voltage regulator, and it has a programmer built in. So of course, our prototype design does not need these things. What we still need is a microcontroller interface that is the same as the one that we've decided to go with. So this is the STM32 L432KC. So I'm going to need a dev board with this chip. And we're also going to need all of these user interface controls because this is the actual application of our firmware. So if we want to prototype and test things, then we're going to have to wire these things up and test them and build our firmware around that. I've gone ahead and simplified the schematic off screen for our prototype. I don't think this really needs much explanation. It should be fairly self-explanatory. All I've done is just replace the surface mount microcontroller with the dev board equivalent, and I've dropped off the power regulation and USB input stage because of course we don't need that. This dev board is going to handle that for us. The user interface controls are wired the exact same way, they go to the exact same pins, and that's by design. This is what you want to do in your prototype stage, so that once we get the PCB, it's pretty much flash and play. You want to capture the main part of your application so that we can actually start building the application in the breadboard, right? And then you can bootstrap from there. Here's our component listing. We don't actually have too many of these to contend with. We've got our LEDs over here, we've got our push buttons in the middle, and we've got our LCD over there to the right, and of course our Nucleo board, our breadboard, and a bunch of wires. So without further ado, let's build this thing. The first thing to do after putting our dev board in the middle of the breadboard is to set up power rails. So if you remember from our design, we only have a 3.3 volt power rail, so that's what I'm setting up here. There's a 3.3 volt output on the dev board, so I connect that to the rails on the breadboard. I set up 2 rails on the breadboard for good measure, and then you can go ahead and connect the ground lines as well. Now I actually forget to connect a ground line here, and I go ahead and add that later. I will point out the pin where that is, and then I just wire up another ground rail on the breadboard as well. I placed the LCD off to the side, and now I'm setting up our push buttons and LEDs. So be careful with LEDs, guys. They do have polarity, so make sure that you plug the anode and the cathode into the correct places. I'll put a diagram up on screen for you to remember. I'm going ahead and setting up our current limiting resistors from the design. So the LEDs are going to have current limiting resistors on them, and the push buttons are going to have pull-up resistors on them. As I actually wire up the LED to the dev board, what I'm doing with the mouse is checking 2 things. The first thing I'm checking is our design schematic, which is going to tell me which pin on the microcontroller it's assigned to. I'm also checking the pin out of the dev board because sometimes the numbering on the PCB of the dev board does not match the actual microcontroller pin it's mapped to. This is why building on breadboards can sometimes be really confusing, a little bit finicky, is because we have this absolutely egregious example where pin A4 on the microcontroller is mapped to A3 on the PCB. What genius thought of that idea? As I wire up the buttons, I need to let you guys in on a trap that a lot of new people fall into, and that is how the buttons are actually electrically wired internally. So you might be thinking, okay, from our schematic, we are simply wanting a single pole, single throw switch. There's one side and another side, and then you just push the button and it closes them. Well, the push buttons that you buy, even in that configuration, will sometimes have 4 legs. And what you'll actually get is that the 2 legs on one side are mapped internally to one side of the physical switch, and 2 legs are mapped to the other one. So you actually have to check the datasheet for your button to get the internal electrical wiring, otherwise you might short them. In this button's case, it's horizontally mapped. So in order to get the 2 sides of the electrical switch, I need to connect one wire to the top and one wire to the bottom. Wiring up the display is a little bit more complicated because we're actually only using 4-wire SPI for this. You'll notice it has a lot more than 4 wires, so there's going to be a bunch that are unused, right? Well, the reference design for this particular LCD says that we actually need to short a bunch of them together and connect them to 3.3 volts in order to satisfy them being unused. So that's what you can see me go ahead and do when I bridge them. And actually in the design, MOSI needs to be bridged as well between 3 different pins. Just a little bit of an oddity for this LCD that makes wiring it a little bit more tricky, but otherwise it's all fairly standard. You just copy what's in the schematic and you pretty much just go from there. There's a backlight power for the backlight, obviously, and then there's also a VDD for the logic chip. So just make sure you plug both of those into 3.3 because that's important, otherwise you'll be having a backlight and no logic, or the other way around, you'll have logic and no backlight. Once the LCD is wired up, we can do the aptly named smoke test, where we plug it in and see if anything blows up. Of course, the reason my own logo pops up there is because I've already written the firmware and flashed it before filming the video, so we're going to go ahead and show you how we get to this point. I know that it's really tempting to want to dive in and start writing firmware straight away, but it's important that we take a step back and consider our firmware architecture. And this is one of the levels that differentiates more novice users between more advanced users, is the ability to actually model your system and sort of understand everything that's going on before actually writing any code. So in terms of firmware architecture, there are 3 things that we need to consider relating to what our system is doing at any given point in time. First one is polling, the second is interrupts, and the third is what our main loop is doing. So we're all familiar with the main loop, right? In Arduino, you might have seen this written as void loop, but typically we just write it as a standard while one or while true loop. A polling is where the CPU is actively checking things, so it might be checking that data is ready in the UART register, or it might be checking some certain flags or conditions that are set by hardware events. Interrupts are where the CPU actually changes context because of an event that happens and actually executes a completely different strain of code. Let's start off with the 100% polling approach, and I want to illustrate why this is something we probably don't want to be doing. So what we've got here in blue are basically like CPU tasks, things that the CPU actually has to do. And inside this big arrow jump is going to be our main loop, so the while one loop that our program is essentially running in. The first thing we do obviously is hardware in it, but inside the main loop, have a look at all of these tasks we have to do. We have to copy ADC data, poll the buttons, poll the UART, handle user input, display, render the image to the display. We have to pass communications from a PC, and then we have to transmit data to a PC. So I want you to think about how this impacts the concurrency of our application. Because what you have to understand is that all of these operations take time. Now, some of these operations are going to take more time than others. What takes more time than others? How do we even quantify that? Well, things that work with big data, or with inefficient algorithms, so think like O of n squared algorithms, are going to take up a lot of CPU time, which is actually a very precious resource in a system that A, has to do multiple things basically concurrently, and B, has limited CPU power to begin with. So keep in mind, we're only on a very small microcontroller here. We don't have gigahertz of compute power like we do on a big multi-core Threadripper or something like that. So we actually have to be a bit clever with how we manage our tasks if we want to achieve relative concurrency. And that's something that an RTOS can help you with, but our project is so simple that I don't think we're going to need an RTOS. So think about these tasks, right? When are we working with big data? First, we can consider this one, the ADC. Well, the ADC is actually going to spit back like a uint32. So that's not actually going to take too much time for us to handle. Sure, it's annoying, but it's not actually going to be a huge hog on our CPU. Polling the buttons and polling the UART is basically just checking a couple of registers and doing a copy. So that's not actually going to cause us a lot of pain either. Handling the user input. So this may, depending on what the action required, is going to have to do. So for example, we poll our buttons back here, and now we actually have to do something with the result that we polled. So if we check the button and notice, okay, it's pressed, then in this section, we actually have to do something with that. So what are we going to do? Maybe we update some display elements. Maybe we enable some functionality. Maybe we disable some functionality. So the complexity of this really depends on what we actually want to do with it. I think in our oscilloscope project, it's not actually going to be that big of a deal. So I'm not really concerned about that. However, rendering the display is going to be a big CPU time sink. Why? Because in this section, we deal with both potentially O of n squared algorithms and also manipulating big data and transmitting big data over SPI. So keep in mind, our display is something like 192 by 96. We're going to need that many bits. So take 192 times 96 and divide it by 8 or something. And that's going to be how many bytes that our SPI bus has to transmit in this step. Also consider that when we're rendering things like UI elements, we're filling rectangles, which is like, okay, O of n squared, right? We have to loop through all the pixels and we have to set them individually to fill out our rectangle. So in this display render step, we're potentially working with a lot of big data, and that's going to hog our CPU. What that means for us is that if this takes, say, like maybe 10 milliseconds, that's going to be 10 milliseconds before we come back and poll our buttons again. So you can see why this is a huge problem. If we push a button while our display is being rendered in this step, our CPU is going to completely miss the button event, and that's going to be a big problem. Similarly, when we pass communications from the PC, we're going to be working with commands, buffers, it's going to have to pass a communications protocol. This is potentially going to impact our performance quite a bit, and the same with data transmission. Now, of course, the solution to all of our concurrency woes are interrupts. Why can I simply not have an interrupt during this display rendering process that then goes and checks our buttons, and then we're off to the races? We've got a very concurrent application. And you're right. So let's take this to the extreme. Why don't we have, for the sake of concurrency, a completely interrupt-driven system? Why don't we do pretty much nothing? You can see our main loop is completely empty here, and we have a completely interrupt-driven system. Surely this would make our application completely concurrent, right? And we just have responding to events here and there, the CPU just jumps all over the place handling things. Why is this maybe not a good idea? You might be wondering like, okay, Hoff, nobody would ever design a fully interrupt-driven system. This is a silly example. It is a silly example, but I want to demonstrate why interrupts are a great tool for concurrency, but if taken too far, they can actually harm the operation of your application. So let's dive in. 100% interrupts, what do we have? We have a completely free main loop. You can see the main loop does absolutely nothing, and we just have interrupts here that do everything. Now, some of these interrupts are going to be okay, right? So if we have an interrupt here where it says our ADC's data is ready, let's just transmit that, and it's a uint32, that's not going to take a lot of time. So we come back to this concept of things that take a lot of time. Now, if we're completely interrupt driven, and we have a timer that's saying like, okay, every 10 milliseconds we want to render a new display update, and we actually do the display rendering in the interrupt service routine, that's going to be a very big problem. And actually, I want to bring this up because I've seen so many students do this. I used to be a TA for an embedded systems course at my uni, and things that I saw all the time were students would have very inefficient code in ISRs. And this absolutely kills application performance because it's no better than this right up here. If you have inefficient code that's in an ISR and the CPU can't finish the ISR, you are going to block other things from happening. So even if I have a hybrid approach, right, where I have things in my main loop, but my system is spending too much time in an ISR, I am actually going to miss stuff in that ISR as well, and it's going to be a very big problem. And for that reason, I generally like to make my ISRs as short as they reasonably can be. It doesn't mean do absolutely nothing in your ISRs, right? It just means that be mindful whenever your CPU executes an ISR, it's branching off from the main loop and doing something completely different. So you're not going to be able to handle main loop tasks while that ISR is being serviced. Just keep that in mind. Now I want to introduce a hybrid architecture that seeks to fix the problems with the previous two that we've discussed, and aims to be the best of both worlds. I'm going to run through this and sort of explain to you why I personally believe that this does address the issues of the previous ones. So what do we have first of all? We start off with the hardware in it, and we do have things that happen in our main loop. Now we have some ISRs over here, and what this yellow triangle represents is a DMA transfer. So DMA is essentially just like memory transfers that occur without CPU intervention. So let's explain this DMA stuff first. So why does this fix a problem with our previous architectures? Well, simply put, this means that our ADC can be operating on its own and can place its result values in the memory of our application without the CPU having to do anything. So we don't have to do this copy ADC dataset, and we don't have to get this ADC interrupt complete. So we've essentially just removed two things from our system right off the bat because we chose to use DMA. So we don't have to worry about our ADC interrupt drowning the system in interrupts and preventing things in the main loop from running, and we also don't have to worry about polling being done in the main loop getting interrupted by longer running main loop tasks like display rendering. I want to cover the main loop tasks, and I'm going to show you how the interrupts I've selected to use help concurrency in this case. So what we have here, one of our first tasks is user input handling. Why is this here? Well, one of the reasons for that is because I think the main loop is probably where it should go, just for state management. So it comes right before the display render, and the user input handling is going to determine a lot of things about the display render. So I don't want them being changed halfway through a display render if it's done in an interrupt, because then I might have display elements that are in the wrong place, or like if channel 1 is set as enabled and there's an icon here, halfway through we interrupt and now channel 2 gets drawn, it might lead to a couple of state issues. So I'm going to have the user input handling in the main loop, but importantly, the source of that is going to come from an interrupt. So basically what we're going to have is a bit mask where it's like, okay, the interrupt is going to set a bit in the bit mask, which is going to be an event that the main loop then checks. I want you to consider a case where this takes maybe like 100 milliseconds. It probably isn't going to take that long, but let's just say for the sake of argument, this takes 100 milliseconds. And the user's button press only lasts for 10 milliseconds. So what we're doing is like, if we're doing this polling architecture, we completely miss the button press because it only lasts 10 milliseconds, and we're spending 100 in this section of the program. So what actually happens if we have this interrupt over here is that even if we're in this section of the program, we still capture that event. So it's been flagged that the user pressed the button. And we get around to handling that here. So sure, like it takes 100 milliseconds for us to get around and handle the user input. But the important thing is that we capture the event. We didn't miss it. We capture the event, and then the next time we get around to handling it. So that might be like, we're not talking about orders of magnitude of like seconds of worth of delay here. We're talking about something that is unlikely to be human noticeable in the worst case. But the important thing is that we don't miss that event. Now, another important thing I've done here is I've split up the receiving the communications versus passing the communications. So it's actually passing the communications that's going to take a lot of time because we're dealing with an entire packet, and we have to do things like CRC checks, retries, all sorts of things like that. Now, what we're going to be doing in this interrupt is just simply receiving things one byte at a time, and we're just going to chuck that in a buffer, and we get a set a flag once received bytes equals length of the packet or something like that. And you could say like, could we DMA that? You're absolutely right, we could DMA that. But I'm going to keep things simple because it's very easy to write an interrupt handler that simply just checks and sets a flag when it's equal to a certain length. And I don't think we really need to worry about that because we're not sending commands from the PC super often. So it shouldn't actually matter too much that this is in an interrupt. So you have to consider the frequency of your interrupts as well, and I don't think it's worth the bother to put this on DMA just yet. The final interrupt I want to go over is this timer interrupt right here, which basically says like flag data TX. What do I mean by that? I want you to think back to the original requirements of this device. This device is supposed to be accurate up to 500 kilohertz. But what that means is we're going to have a reasonably high data transfer rate, and we're going to need to be storing our data in a very efficient way. One of the cool things that we can do with DMA is called increment memory. So what that means is like we can just have a buffer where all of these values are going into, and each time we do a DMA transfer, it's going to increment that. So what we want to be doing is just continuously, and of course it'll loop back to the start when it's done. So what we're going to be doing is just continuously filling this DMA buffer with information, and according to our timer interrupt, which is going to be specifying that boom, 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 like 500 kilohertz interrupt, we're just going to go ahead and mass transmit whatever's in this buffer over to the PC, and that's going to be done in the main loop over here like that. So what we're doing is we're not wasting time doing copies, like in this we're not wasting time doing copies, and basically it's just like we're continuously filling this buffer automatically, and whenever we get around to it, we're just going to go ahead and mass transmit all of that information. So that should be I should be pretty happy with that. I haven't set that up at the moment in the prototype stage. It's literally just like as soon as it gets to send 1 byte or 1 DMA value, it goes ahead and does that. But we're going to get into more advanced stuff later on in the next video. I introduced STM32CubeMX in a previous video. Pretty much what it lets us do is configure all of the hardware for our device, and it will actually generate the hardware initialization code for us. It's really cool. So we can graphically go ahead and configure all of our hardware, and then it'll generate the code that actually implements that as an abstraction layer on top of just like setting registers and stuff like that. Now, I would actually recommend you learn how to deal with register setting if you haven't already, because this is an abstraction on top of that. And if you don't know what's going on under the hood, when you encounter a problem with the hardware abstraction library, you will not really know what it's doing and you won't really know how to deal with that. So I would recommend learning to set registers, but for more complex projects and in industry, we generally use generator tools like this to save time. But it can bite you down the road if you don't know what they're doing under the hood. Now, I'm not actually going to teach you how to use CubeMX in this video. There are great resources online, for example, like Deep Blue Embedded. If you search up like STM32 timers in CubeMX, it will come up and it'll show you exactly what steps you need to do, like to click on the timer, it'll explain all of the settings to you. But what I want to get through to you in this series is like how to design the system, how to come up with the architecture of the system, and then in CubeMX is where you pretty much just go and implement that. So I'm not going to waste your time showing me just clicking through enabling GPIO interrupts for like 20 minutes when you can just Google, like based on our architecture that we've come up with before, we already know we need a timer interrupt. We know we need GPIO interrupts. We know we need UART interrupts. So you can just Google like STM32CubeMX GPIO interrupt and Deep Blue Embedded or something else will show you how to do that. One thing I want to note is that these pin assignments have changed from the schematic, and I will issue an updated schematic. The reason for that is because my Nucleo board on here is like a little bit cooked and some of the pins don't actually work the way that they should. So I've had to, after I did the wiring that you saw me do earlier on in the video, I've had to mess around and sort of like rewire it until I found pins that all worked. So because some of them would output like low logic levels and stuff, it was really weird. And yeah, but anyway, we got it sorted. I've changed some of the pin assignments. Don't freak out about that. Just follow this. I'll issue an updated schematic. It'll be in the description. So if it doesn't match what you've seen previously in the video, don't freak out. This sort of thing happens in the prototype stage. You know, you put things together, you wire things up, and then after that, you realize there's some problems and you have to go and issue revisions and make changes. That's what this stage is all about. So just don't freak out, all right? This is the structure of an application that Cube goes and generates for us. The ones that I've highlighted are generated by Cube and managed by Cube, and the ones that are not highlighted are my own code and stuff that I've added. If we actually go ahead and dig into core and source, we will find main.c. If we open up main.c, I want to give you an idea of what Cube generates for us. This is pretty much just like hardware initialization, you can see, that is based on the setup that we did in CubeMX. So it'll generate all of the hardware initialization stuff for us as we defined it graphically in CubeMX, and that is what makes it such a great utility. So it pretty much, you can see here, for example, it's setting up this timer, and it's setting up the period that we selected and all of the settings that we selected as well. Now, one thing I will say is I actually don't really like playing in this file right here. So this is main.c, but I actually don't like it. You can see here that the way that it gets around regenerating stuff is it has all these user code begin things. I don't like to play in this sandbox. I want to break out of it. So the way that I architect my STM32 project is I use cube, and this main.c essentially just becomes a big hardware initialization file, and then I break out of that as soon as I can. So you can see here, after cube does all of its hardware initialization, I actually run my own function, and we never reach cube's while one loop, because this is basically my app entry point. If I go on over to here, you'll see our real while one loop that's executing over here. And this is in my own folder, right? So this is all cube stuff, and this is my own folder where my own code goes. So this is just to keep things a little bit more organized. I generally don't want to live in this file right here because cube's going to regenerate things and it's going to change all the time. I want to live in my own little world. And an important thing to be able to live in our own world, you can see cube has all of these handles for the various hardware devices. Well, what we want to do is just define pointers to those in our own structures, and then we can just go ahead and set them right here in the main one, so that we never have to go back and hash include this main file. We never have to do any of that stuff. Our application simply has the type defs that it needs as pointers, and it's just set here right at the beginning. The next part of this video is going to be going through this firmware and explaining how it implements the architecture we talked about in the previous section. We're going to go through the modules that we've made and how all of the event flows, like the interrupts and then the polling and the main loop and stuff, how that all interacts and actually implements that architecture we described. Now, the first thing I want to talk about are these modules. So I made a couple of modules here. Mainly, we have channel data, channel management, and small scope app. I have 3 modules at the moment. So I'm trying to keep this very simple. There is something to be said about coupling between modules, right? So when we are making new modules, we generally want the coupling to be kind of low. Although what I will say is this, in embedded systems, coupling is inevitable because everything in the system is so interlinked. Like, things that happen over here have to influence things that happen over here. You're going to get coupling. The idea is to manage that coupling in a sensible way. And the way that I like to do things is I have a top level file. So this small scope app is the one with the main loop in it, right? It's going to be doing a lot of the just general tasks and checking things from our modules and sort of tying things together. So I like to think of this as the file that sort of implements or calls things from all the other files, so that the other files don't necessarily have to interact with each other. So what we have is this. Now, if we go to channel management, the point of this, now remember, we're trying to design an oscilloscope. So the point of this is to actually define channel management, which is basically like, okay, which channel is recording, which channel is enabled, which channel is displaying on the LCD. It's just displaying implementing the application features of our channel. So you can see in this channel management, I have things like the record button callback, the button 1, channel 1 callback, channel 2 callback, and I have logic here for toggling individual channels. So let's see how these are called. These are all called by interrupts, right? So if I go back to main.c, and if we scroll down a little bit, you'll see that Cube has generated some callbacks. So here is a GPIO external interrupt callback. And you can see the way that Cube does things is you get one callback function and you just switch on the GPIO pin and you run things based on that. So if we get an interrupt on our GPIO button channel 1 pin, it'll call this function. And you can see this function here. What we do is we implement a very simple tick-based debounce and we set a bit mask flag. So I have this button events flag defined up here. It's marked as volatile so we can do it interrupt safely and the compiler won't optimize it at all. And we just simply OR equals it with this event. You might be wondering, why is this a U32? The reason for that is because in STM32, operations on U32s are atomic, meaning they take one CPU instruction. And so that means we can set and check things, and generally it will be race condition safe as long as we don't do something silly with our application logic. And so you can see it's actually dead simple to implement that flag in the ISR, check and handle in the main loop, and it ensures that our application remains responsive to user events, even if the CPU is busy doing something else when that user event happens. Let's talk about data. right? So we've got this whole idea of we want this logging functionality to go to the PC. Like we want to get our ADC samples in and transmit that to the PC. What is that going to look like? Well, in this module channel data, I have actually defined some communication structures, and this is how we're actually going to be transmitting things to the PC. The first thing I've done over here is I've defined a struct that represents our communication packet, and what we're going to do is send this data exactly as is. So I'm not sure if you guys are aware, but structs in memory are actually contiguous. Essentially, you can cast them to a uint8 buffer, like a byte buffer, and you can read and write them and memcopy them and do all of these things. So in order for speed, what we're going to do is we're going to have this packet directly defined like this, and I've got this uint16 channel thing in here, and what our ADC is going to do is basically just DMA straight into here, and we're going to transmit right off the bat. Now, this doesn't implement our buffer strategy we were talking about in the architecture section, but that's okay. Just for this prototype, I just want to get anything sent to the PC, right? Like, the whole point of what I'm doing now is, can I boot up the ADC? Can I define a packet structure? Can I send it to the PC? Can I have the PC decode it and display it? So for this, what we have is just a very simple message, like message type, like this is data, like this is ADC data, or this is like a command, or this is whatever, the length, the channel, and a CRC. It's a very simple communication packet. We're just going to directly transmit this. And what I mean by that is literally, like if you look in here, this is our channel data transmit callback. I literally simply cast this channel data struct, which is, an instance of this structure right here. I cast this to a uint8 buffer and we send it. That is how simple it gets, guys. This was a big realization for me, is that everything is just uint8s. It's all bytes. Everything is always bytes. I'm going to do a follow-up video on this kind of concept, but everything is just bytes. We can cast it to a byte buffer, we can send it off, and as long as we know how all of these are encoded, like they're just U16s, right? So we can simply decode them on the PC, then they're going to come in as a byte array, and we can just decode them because we know the length. We know this one's 16, this one's 16, this one's 32, 64, I think. This one's 32, etc. And we can just decode it straight from there. And you can see here, this is our struct ch data, and I have it externed here, right? So other modules can access this. We go back over to this small scope app, so our main loop basically. You can see here, I'm starting the DMA from our ADC, and I'm pointing it directly at this struct value. So what that means is our ADC is going to DMA straight into this struct, which is then, like according to our timer flags, is going to get sent straight off to the PC. Another thing you might have noticed in here is this ch event flags that gets toggled on the ch timer update callback. Now this, if we go back over to main.c, we'll find this HAL time period elapsed callback, where you can see here, if it's timer 16, and what I did in Cube is I set up timer 16 to basically just be the like, okay, you can transmit something now. It'll call this, which literally just sets the flag. So what we're doing is that whole like ISR flag setting, and then our main loop is going to check that right over here and call this transmit callback. So pretty much what we're doing is the same thing as these button events, but instead of a button or user interaction, this is just timer. So boom, 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 boom. It sets that event flag, and all that does is call this function that just transmits our ADC reading to the PC. So that's pretty much how we've structured the first parts of our architecture. We get that back up. We've shown how we use this, albeit without the buffer strategy. It's just boom, just transmit whatever you've got right now. We've shown the GPO button event handlers. And this UART USB from the PC, I'm actually marking as not implemented in the prototype stage because it's out of scope. So I haven't actually set that up, but it's not very important because we've reached our MVP of we can transmit ADC readings to the PC. We don't really care about the command interface just yet. That's going to be defined after the prototyping stage. So we've sort of shown all of the main interrupts, the DMA, and some of these. What I have here is a display driver for our LCD. And what I'm not going to do is actually show you guys how to write this, because I already have a pretty much 1 hour length video on how to write a display driver, albeit for a different LCD. What I care about is teaching you guys the process, not necessarily giving you a step-by-step copy paste exactly what I do. So instead of wasting your time and wasting my time shoehorning in an explanation of this code into this video, you can check out my 1 hour video on how to write a display driver. It covers vector graphics, frame buffers, bitmaps, fonts, everything that you want in a display driver, and how to adapt manufacturer code into your own sort of application, which is basically what I've done here. So there's nothing much to say about this except we've got send a command, send a data, set pixel, draw a bitmap, transmit the frame buffer, etc. And it's as simple as that. This is all the code that we need, 167 lines, to display a simple bitmap image on the screen. And you can check out my other video on how to write a display driver if you want to learn the process of how to do this kind of thing. Even though I won't be showing you how to write the display driver in this video because I already have a full video tutorial on it, because this is a prototyping video, I want to introduce you to one of these. This is a logic analyzer. These things are incredible. Basically, what this lets you do is capture, record, and analyze the signals of your communication buses on your embedded device. So for example, as I'm writing the display driver, I can hook this guy up to the SPI bus and actually analyze and make sure that the commands that are being sent are correct, in the right order, in the right format, with the right timing. And that way I can double check that with the datasheet and also with my other references like existing code, and I can make sure that my device is emitting exactly what is required to get that display to light up. By the way, what I'm using here is a Sele Logic 8. They're actually kind of expensive. Like this one I think is 800 Australian dollars. You can get student discounts though. So if you're a student currently in university or a hobbyist and you're not going to use it for commercial purposes, you can buy one of these at a pretty good discount. I think it's like 50%. So I'll link that in the description. It was expensive still, even with the student discount. I got one of these to do my electronics engineering thesis, and it was expensive, but so worth it because now I'm using it in my like hobbyist projects. I can use it to show you guys how they work in this video it's amazing. And so even though it still cost a lot of money with the education discount, I think it was fully worth it. I would buy one of these again and again and again. Now over here in the Sele Logic software, I'm just going to drag my face a little bit so you can see what I'm doing over here. What we're doing is basically enabling a SPI analyzer. So what we can go ahead and do is enable channels 0, 1, and 2, because those are the ones that we've sort of already decided to use when we did the wiring. And what we can do is go over to the Analysers tab, and I already have one here, so let me just delete that. We can add a SPI analyzer. And so it's going to ask us some basic things like where is Mosey? Drag myself back over again, jeez. Where, like, which one's Mosey, which one's Miso, which one's clock, blah, blah, blah. So for this one, I've set channel 0 to be clock. I've set enable to be the red one, channel 3, and I've set Mosey to be channel 1. If we go ahead and hit save, these ones, you can verify that in Cube. Actually, these are going to be 0 and 0 because we're intending to use SPI mode 0. So go ahead and hit save, and if I go ahead and hit run, it's going to start recording right now. And now what I'm going to go ahead and do is unplug and replug my device so it does the startup process again. And boom, you can see we just got a hit for some data. We go ahead and scroll in here, you can see our clock is going boom, 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 boom. Our Mosey is like this, and our chip select pin is going up and down depending on when we're sending information. And so we can actually verify that this is showing up. So what I want to do is scroll all the way to the start, and we'll check 30 and 94. We go to our code, and we go back to right here. One of the first things we should be doing is sending 30 and sending 94. So we can verify using the logic analyzer that this is actually correct, and we're sending that. We can also scroll, like if you go over to here, this is when we actually start to transmit our frame buffer. So if you are really so inclined, you can check the values of all of these match up with the image that you have currently in your frame buffer. And you can just use this to debug. So if we go in here and we think about when these bits are going to get clocked, so you can see here, like based on the clock lines, when this bit is going to get clocked. And so that way you can debug your like timing, like compare this little picture right here with your datasheet and make sure you're operating in the correct SPI mode and things like that. The logic analyzers are really, really good. You can also, because it gives you a timing readout here, you can see like 1.4 microseconds, You can also verify that your timing is within spec for your device by comparing with the datasheet. So these things are really, really useful, and I'd get one if you can afford. The last thing we have to run through for this demo is this Python file right here. This is actually a script that's going to run on our PC, and the point is just to receive those ADC values that we're transmitting, decode them, and plot them in matplotlib. So you can see what I've defined up here is, for example, our channel packet, and we have this very simple decode function that takes advantage of the fact that we know the exact size of our bytes in our byte stream. And what we go ahead and do is just decode them. Pretty simple. I don't think it really needs much explanation apart from the fact that maybe the bytes transmitted are little endian because they're coming directly from our microcontroller's memory and our microcontroller is little endian. So our receiver has to do a little bit of reconstruction here, but not too much. Then we just have a serial read thread where we're reading from it. So the Nucleo device that we're prototyping with has debug UART, and it shows up as a COM port on our PC. So what I've got here is just PySerial, like pip install PySerial, and we're reading constantly from this and just extending this big like data. So I have ch1 data, ch2 data, and these are both arrays. And, we just continuously add to that as we get data in. I also have, now I asked chat how to do this because I have no idea about matplotlib. So chat has given me like a little updating script thing to continuously update the matplotlib animation. But yeah, so this is our simple, it's like under 100 lines. It's our little demo application for receiving, and I'm going to show you guys how it works because it's really cool. What I've done for this demo is I've wired up one of the ADC pins to the button for channel 2. So you can see I hit record there, so it's streaming data to the PC now, and the red light is on, and I can go ahead and select the channels, like press the buttons for the channels. You can see the LEDs for the channels light up, and it's responsive, like it's handling these events while streaming data live to the PC because of our design. And you can actually see as I push the button for channel 2, you can see our ADC actually record the button events. You can see it's going from 4000 to 0. 4000 is the top end of the ADC and 0 is the bottom. You can see there's a little bit of noise on the top end of the ADC. So that's when it's, reading just a constant value. There's a bit of noise there. So we can investigate that later. But as soon as I, push a button and get it to go to 0, it goes away. And you can just see me starting and stopping the recording there to show that that functionality is in fact working. It's very, very cool to see this working, and it's really cool how responsive it is. And with that, our prototype is actually fully complete. So what we achieved in this video was we wired up our prototype according to our schematic, and we validated all of the hardware is working, and we validated our schematic design. We've implemented a base firmware architecture that is going to be expandable for us in the future when we decide to put in more advanced functionality. We've developed an MVP where we have data streaming working, going to the PC, and we've got recording, starting and stopping, all of that good stuff. So we have the basics of a communication protocol. We essentially have a baseline to fully develop the rest of our product. And we also have confirmation that we can go and do a PCB now that we know that the base wiring is fine. So if you've made it this far, I just want to thank you. This has been a mammoth of a video to create. There's going to be one more on the way where we do a PCB design and finalize all of this. I hope you've enjoyed coming along for the ride, and thank you so much for checking this out.